Okay, so we're back, and now that we know a bit about how it was determined what rocks actually meant, and how rather than being just bits and pieces that are from the formation of the Earth, they actually formed throughout a very long history of our planet, and therefore they can tell us quite a bit about the history of our planet. So now that we have that figured out, so we will get into what the Earth is made of in the first place. Okay, so to understand what the rocks are made out of and how the different compositions and textures of rocks can tell us about the history of our Earth, we first need to understand a bit about what the Earth is made of in the first place. So these are the most. So over here on your left is the most abundant minerals in the Earth's crust, and these are made up of the most abundant elements in the Earth's crust. So it surprises a lot of people to find out that the most common elements in the Earth's crust are oxygen, which is like a gas. So how can that make up the majority of rocks that we have in Earth? That seems strange. And silicon, which and these are really the dozen or so elements that geologists focus on. We don't have to know, like if you're a chemist, I guess you have to know about the whole big periodic table. We just have like, about 12 or so that are very important. So there are things like aluminum, then iron, calcium, sodium, potassium, and magnesium, and everything else, including carbon, makes up only about 1% or so of the abundant elements in the Earth's crust. So as we're looking at these elements, primarily oxygen and silicon, we could be thinking of, okay, what minerals are we looking at? Well, it's not too surprising then that most of them are silicates, which means they contain a lot of oxygen and silicon. So as we go over here to the chart on the left, the most abundant minerals in the Earth's crust, we have a lot of some weird words here that we're not too familiar with, but we're going to be looking at feldspar quite a bit. It's a very important mineral and obviously a hugely abundant mineral. So feldspar itself makes up about half of the minerals in the Earth's crust. A couple different kinds of feldspar here. We'll kind of learn how we're not, this isn't really a rock and mineral identification course. Take Geology 110 for that. But we will be talking about some of these things and what they mean. And then there's quite a bit of quartz, which is like the ultimate silicates because it is just silicon and oxygen, nothing else. Whereas the feldspars have a lot of silicon and oxygen, but a lot of other elements too. And then we have pyroxenes, amphiboles, all sorts of different groups that sound kind of funky. And yeah, almost all of these are considered silicate minerals. So they contain oxygen and silicon as their basic building block. And then a whole lot of these other elements too include. So we're going to be looking mostly at silicates, and we'll start to look at that a bit today. This course, we're really just focusing on a few rock forming minerals, which are really important because they're going to form the majority of rocks that you see on the Earth, and obviously the majority of the rocks that we use to study Earth history. So by far, the majority of these are going to be silicates then, silicon and oxygen bonded with a bunch of those other elements. So from Half Dome in Yosemite National Park, which is made up of these minerals, is made up of granite, and granite typically contains a lot of feldspar as well as a couple other things. Or we could be looking at some ancient desert dunes in Arizona and California, and these are made up of quartz. Most sand on Earth is made up of quartz, unless it's biological and there's shells in it too. Like in Florida, that's a different story. We'll get into that a little bit later. But it's most sand is made up of quartz, and the reason why it's red is because it's stained like with a rust with iron oxide. And then we could be looking at, so those are mostly silicates. And then as we look at some other groups of minerals like the halides, then we're looking at some salt flats here, which are made up of the mineral halite, which is sodium and chlorine, sodium chloride. This is salt, very, same thing as what's in your salt shaker at home. So the salt flats around Salt Lake City, that's exactly what they're made out of. And this mineral forms very, very differently than silicate minerals do. We're also looking at carbonate minerals like what we see here in Kentucky. So this is some limestone along a road cut in Kentucky, and it's made up of a mineral called calcite, which is calcium carbonate. And it's not just going to be crystals of calcite, though limestone is often that too. Many kinds of limestone that we see, including here in Kentucky, are a type of biological limestone made up of the bits and pieces of broken bodies of animals, seashells and coral and plankton that use calcite to create their exoskeletons. And then as they die, that settles down and becomes limestone. So we're looking at a lot of silicate minerals, but a couple other important groups are salts, like the halides, and especially here in Kentucky, some biological sediments, the carbonates, like calcite. All the other minerals, anything that's important, that's an important metal ore, like galena or pyrite. These are all tend to be accessory minerals and are much more minor, but they can still be, because they can be quite rare, they can be really important to tell us Earth history as well. So, and you know a bit about how the Earth formed, where all the heavier elements kind of sunk down toward the center. So that's why the core is made primarily of heavier elements like iron and nickel. And then as the Earth continued to spin, it's flinging the lightweight minerals, or lightweight elements, I'm sorry, out to the crust. So that's why our crust is made of some very light elements, including oxygen and silicon, especially oxygen and silicon. Then, of course, aluminum, sodium, and potassium. So somewhere in between is our mantle, which is a mixture of a lot of these, but does contain a lot of heavier elements like iron, magnesium, and calcium. So because of that, there are rocks that form deeper in our Earth. So things that make up, for instance, the oceanic crust or the upper parts of the mantle are going to contain more iron and magnesium and calcium than rocks and minerals that make up the continental crust, which are going to be made up mostly of lots of silicon, lots of oxygen, aluminum, sodium, and potassium. So when we find a rock of a certain makeup, that can help us determine what part of the Earth it came from. And that's kind of a little introduction into igneous rocks, because we're going to be looking at two major igneous rocks here, basalt and granite. And the reason why we're picking these out right now, before we even get into the rocks, like we will in a few minutes, but we are going to take these because they make up the majority of the crust of our planet. So basalt makes up the oceanic crust primarily, and it's made out of a little heavier minerals. These are we have quite a bit of feldspar as well as some of these others, and they contain a lot of iron and magnesium and silicon. These are silicon. These are silicate minerals, so there is a lot of silicon and oxygen here too. But then as we get into granite, we have some lighter weight and therefore lighter colored minerals that have a lot more silicon and oxygen, and also contain things like aluminum and potassium and sodium, not the heavier elements like calcium and iron and magnesium like over here with basalt. So that means then that the entire rock are going to be different densities, they're going to be different masses, and they're going to float differently in the Earth's mantle. So continental crust then, made of granite, is going to be lighter weight than oceanic crust, which is made out of basalt. So the crust is made out of rock. The rock is made out of minerals. The minerals are made out of elements. And the weight of all of those things means that these crusts have different masses, so they float differently. So this is one reason why continental crust floats higher in the Earth's mantle than oceanic crust, which kind of sinks down and kind of sits pretty low. And that means that when we have collisions between plates, when a continental plate, and we'll get into plate tectonics in a couple weeks, as we have a continental plate colliding with an oceanic plate, every single time that oceanic plate, because it's heavier, is going to dive down below the continental crust because it's heavier. So it's going to sit lower in the mantle and it's going to sink below the continental crust. So I'll go ahead and show kind of an introduction to plate tectonics that we'll get into later, of course. But we're looking at so we have our convection going on, so our material rising up, and it's creating a spreading ridge. And this is where we have, not to get into the terms too much, but that's where new oceanic crust is being created. And then oceanic crust is diving down below adjacent crust on kind of the sides. Now, this is very idealized, but we'll stick with it for now. We'll get into some more real life examples of what's happening later on. So, and this is I'm going to just pause it right here. So this is a really good example of the oceanic crust sinking down below a continental plate or another oceanic plate. That happens too. And this is called a subduction zone and is where most of the deadly volcanism and a lot of the big earthquakes of the world occur. So again, those two different plates are determining what happens with at plate tectonic boundaries because of their densities. And as that oceanic crust descends, it eventually heats up, begins to melt, and is a conduit for volcanoes that are up on the other plate, which is probably a continental plate. So this is the same kind of volcanism we have in the west coast of North America, like Mount St. Helens. This is a very common way that volcanoes are formed. So anyway, so that's a little bit about the things that make up the Earth. And as we get into the different kinds of rocks in a little bit, we're going to dig deeper and talk about how each specific rock type tells us different things about the Earth's history.